Okay, hi. In this video, we are going to solve some triangles, and some of these might be Pythagorean triples. Sometimes we might have to use Pythagorean theorem to find the missing side length, but basically we want to use the appropriate trig ratios for finding the measures, and then find the measures to the nearest tenth with our calculator. So they want us to find the measure of angle A. So if we look at what we're given, now remember ratios, we have SOHCAHTOA. Some old hag came around here to offer apples, and we just have to see what we're given in terms of patterns. So with A being our reference angle, 6 is an opposite, and opposite the right angle, we have our hypotenuse. So we have an opposite with a hypotenuse. That means we have to use sine. Sine goes with opposite hypotenuse. So sine of A is equal to 6 over 8, which is 3 over 4, which is 0.25. So we have sine of A is equal to 0.25. So we want to find the angle measure that the sine is 0.25, or where the sine is 0.25. So we have to work backwards. We have to do sine minus 1 of 0.25. So sine minus 1, inverse sine of 0.25, then is going to give us the measure of angle A, which is what we're looking for. So I'm going to put this is an older calculator, I'm going to put 25 in the calculator. Then I'm going to do second sine, which is my sine minus 1. And I get 14.475. They want this rounded to the nearest tenth. Rounded to the nearest tenth, we have 14.5. So measure of angle A is approximately 14.5 degrees. Let's look at number 2. We got a 12 and an 8. So they want us to find the measure of angle C. So 12 is a hypotenuse, and this 8 is an adjacent. So we have adjacent over hypotenuse, which means we have to use cosine for this one. So we're going to set up cosine of C is equal to adjacent over hypotenuse, 8 over 12, which is 2 over 3, which is 0.6667. So to find out what angle C is, we have to do the inverse cosine of 0.6667. So this is like looking up in a table. If you know what the decimal is, you're looking up the angle that matches that decimal. That's where the inverse operations come in. So I'm going to put 0.6667 in the calculator. And then I'm going to do second cosine to get inverse cosine of that. And it comes out 48.2 when we round it to 1 decimal place. So the measure of angle C is approximately 48.2 degrees. Okay, let's go to number 3. For number 3, we've got a 4 and a 15. We want to find the measure of angle B. So 15 is an opposite, and 4 is an adjacent. The hypotenuse would be here. We don't know the hypotenuse. We could find it with Pythagorean theorem if we needed, but we've got enough to do this problem. We've got an opposite with an adjacent. That's a tangent problem. So we're going to set up tangent of B is equal to opposite, which is 15, over adjacent, which is 4. So 15 divided by 4 comes out to be 3.75. So to find out what angle B is, we want to do inverse tangent, tan minus 1 of 3.75, and see what we get. So I've got 3.75 in there already. I want to do tangent minus 1 of that, second tangent. And it comes out to be 75.068. Rounded to one place, that's going to be 75.1 degrees is the measure of angle B. So measure of angle B is 75.1. Let's do number 4. F is our angle of interest. 30 is a hypotenuse. 9 is opposite. We have an opposite with a hypotenuse. That's going to cause us to have to use sine. Sine F is equal to 9 over 30. Now 3 comes out of both of those. That's the same as 3/10, which is 0.3. So sine of F is 0.3. The inverse sine, sine minus 1 of 0.3, is going to give us measure of angle F. 0.3 second sine gives us 17.45. Rounded to one decimal place, 17.5. So number 5. Angle Z is our angle of interest for this one. And here's the hypotenuse. 7 is opposite. 13 is adjacent. So we got an opposite with adjacent set of numbers given to us. Opposite with adjacent means we're going to use tangent. Tan Z is equal to 7 over 13. Now 7 divided by 13 is 0.5385. And I want to do tangent minus 1 of that to get the measure of angle Z. So when I do second tangent, I end up with 28.3. Okay, over here, number 6, we've got an isosceles right triangle here. So this is a 45, 45, 90. Instead of doing the trig ratios, like we could do 12 over, 12, and hypotenuse is going to be 12 radical 2. Basically, because of the pattern, angle G is going to be 45 degrees without having to do any work, because we got a right triangle, isosceles right triangle. These two angles have to be congruent. They're complementary. They make up the other remaining 90 degrees using triangle sums. Lots of different ways to know that those are 45-degree angles. So special pattern, recognize that, not have to do any extra work. Let's see what we got on these now. Okay, here we got to find both angles. So since this is a right triangle, what we can do is when we find one angle, we can do 90, take away that angle, and find out what the other angle is, since these have to be complementary. So we don't really have to do two separate trig problems for this. So let's use, say, this one here, y. The opposite is a 21, and the adjacent is a 15. This is 3 times 7. I'm always double checking to see if I can figure out if I have a Pythagorean triple. We don't. Nothing would really matter for this one, I don't guess, just out of habit. We have an opposite. Using y, we have an opposite with adjacent. That's going to be a tangent. So tan y so tangent y is going to be opposite over adjacent. We get 21 over 5, or 21 over 15 rather. 3 goes into these. It's going to be the same thing as a 7 over 5, which is going to be 1.2. So what I would need to do is, or what we need to do is do tan minus 1 of 1.2 to see what angle that comes out as. So let me clear this. 1.2. And we're doing tangent, so I do second inverse tangent. And we get 50.2 when we round to the nearest tenth. 50.2 degrees is what y is. So now if y is 52 degrees, since this is a 90, to tell us it's a right triangle, this only works with right triangles, this method here. These two have to be complementary. So if we do 90, let me change the sign on that. Just change sign key. And then I'm going to add it to 90 to find the difference. And it turns out 39.8 then must be angle x, because together these angles have to add up to 90 degrees. Now the other way to do this would have been to do tan x equals 15/21, and then when you ran it into the calculator you get pretty much the same thing. Okay, let's look at number 8. If we're using angle y here, we have an opposite over hypotenuse, that's sine. So we're going to say sine y is equal to 14/17. Y then is going to be sine minus 1 of whatever 14 divided by 17 is. So 14 divided by 17 is 0.8235. When we do sine minus 1 of 0.8235, inverse sine, we get 55.4. So now if y, the measure of angle y, is 55.4, if we subtract that from 90, we're going to find its complement, which is going to be angle x. And we get 34.6. And together these do add up to 90. Let's look at number 9. Let's see, number 9. Let's use angle x here. W is an opposite, and 61 is hypotenuse. So opposite hypotenuse, we could use sine. We could also use adjacent with hypotenuse. We could use cosine. And we got our choice of either one of those. So let's go with cosine. So adjacent side to the x is 11. The hypotenuse is 61. So we would set up cosine x equals adjacent 60 over hypotenuse, which is 61. So cosine minus 1 of whatever 11/61 is a decimal. 11 divided by 61 comes out to be 0.1803 is going to be our measure of angle x. So if I do second or shift cosine, which is cosine minus 1 of that, I get 79.6. So if x is 79.6, we know the measure of angle x. Now we could define w, do like a tangent, but we would be using a computed value, which might be legit for this. But the better thing to do is try not to use computed values. So this is a right triangle, and we could do Pythagorean theorem to figure out what w is. So hypotenuse squared, 61 squared, minus 11 squared. Take the square root of that, and that's going to be w. So 61 squared minus 11 squared is 3600. That's going to be 60. So this actually is a Pythagorean triple. 60 is going to be w, the square root of 3600. So we use Pythagorean theorem to find out that this is 60. So this is the 11, 60, 61 is a Pythagorean triple, which is probably not known by too many people, but it does come out that way. And let's look at number 10. So for number 10, let's see what we got. They're telling us, again, it's a right triangle. So there's the right angle. This is hypotenuse. We need to find side Z, and we also need to find angle Y. So let's go for the angle first. Let's see. If this is the hypotenuse, this 48 is adjacent. So we have adjacent with hypotenuse. It's going to be cosine. So cosine Y equals adjacent, which is 48 over 52. So if we do 48 divided by 52, we could simplify that, but it doesn't really matter. 48 divided by 52, we get 0.9231. So inverse cosine minus 1 of 0.9231 is going to give us the measure of angle Y. So if I do second or shift cosine to get cosine minus 1, we get 22.6. So angle Y has a measure of 22.6. Now we could use this computed value, and Z would be an opposite, and 52 would be a hypotenuse, and we could actually do sine 22.6 is equal to Z over 52. But it's better not to use computed values. And if we look at what we got here, we got a hypotenuse and we got a side. So hypotenuse squared minus side squared is going to give us the other side squared. So we're going to do the square root of 52 squared minus 48 squared. And that gives us 400, which means that the square root of 400 is a 20. So we have a 20, a 52, and a 48. Now this has got to be a Pythagorean triple. Let's see, what's the common factor for all of these? 4 goes into all of these. That's going to be a 12. That's going to be a 5. And then this is going to be a 13. So this is basically a 5, 12, 13 Pythagorean triple. Now if we recognize that early on by doing the factoring and saw that, then, and we knew this Pythagorean triple pattern, we could have done 4 times the 5 and got the 20 that way without resorting to the Pythagorean theorem. So that's how that would have been a shortcut. Okay, last one here, number 11. We got a 12 and a 15. So let's see what we got. We got 400 times 3 here for 12. We got 5 times, let's do this one. We got 4 times 300 to be 1200. We have 5 times 300 to be 1500. And they're not even asking us for this side. But this is going to be 900. This is going to be a 3, 4, 5. Pythagorean triple triangle. For this one, though, they're not asking us for the side lengths. They want to know what these angle measures are. So going with what we're given, if we're going to use angle Y, this is hypotenuse. The 1500 is a hypotenuse. And in relation to Y, 1200 is adjacent. So we have an adjacent over hypotenuse, which is a cosine. So cosine Y is equal to adjacent 1200 over hypotenuse, which is 1500. That's the same as like a 12 over 15, which is the same as a 4 over a 5, which is a 0.8. So if we do cosine minus 1 of 0.8, we're going to find the measure of angle Y. And then the plan would be to subtract from 90, and that's going to give us the complement, which is angle X. So 0.8, the second cosine of that gives us 36.9 rounded. So if I change the sign on that and add that to 90 to find the complement, which is the other angle, we get 53.1. So measure angle X is 53.1 and measure angle Y is 36.9. Okay, so in this video we basically used some random triangles that were already pre-made random triangles, and went through and we kind of talked our way through sine, cosine, and tangent, and how to do to find the angle measures using inverse sine, cosine, and tangent depending on the situation. And we also looked at Pythagorean triples as shortcuts, and also the Pythagorean theorem to find missing side lengths is possibly a shortcut also. Okay, thank you for watching. If there's anything else you'd like to see, let me know.